Hello all, welcome to the webinar series of IEEE Joint MTT APMC CAST Joint Chapter. I'm Dr. Anushirwan, the chair of the chapter, and I am also working as Associate Professor at Research Institute for Microwave and Millimeter Wave Studies, RIMS, at National University of Science and Technology, Islamabad, Pakistan. So Islamabad is the capital of Pakistan. It is among the beautiful capitals in the world. It has both natural beauty and the business hub, and it is a place where we will conduct our first a dedicated IEEE conference on microwave antennas and circuits this year in December, on 10th and 11th of December, and hope many people from you will join us in physically as well, and also in the virtual mode. So this is a bird's eye view of NUST Islamabad campus, and it is a very well managed campus, and the RIMS building is here. The RIMS, also known as Research Institute for Microwave and Millimeter Wave Studies, is a specialized postgraduate institute that offer master and PhD program in RF and microwave. We're also starting a new stream in integrated circuit design from the next semester. We, apart from foreign faculty, we also have the state-of-the-art research facilities, including anechoic chamber that works up to 40 gigahertz. We have electromagnetic compatibility interference lab, and also micro research antenna lab and PCB fabrication lab under one roof. The idea to have such facilities under one roof is to give an opportunity for the students, apart from gaining their theoretical knowledge, they also get hands-on experience using all these facilities. So keeping in view this pandemic going on, we started the webinar series as a knowledge sharing platform in March 2020, and this is our webinar number 31, and we are very pleased to host Professor Ruonan Han. He's also the distinguished lecturer at MTT Society. He belongs to Department of Electrical Engineering and Computer Science as Massachusetts Institute of Technology, MIT, USA. The title of the talk is Chip Scale Wafer Wave Matter Interaction at RF to Light Frequencies and its application to circuit systems. A few words about Professor Ruonan Han. He received his BSc degree in microelectronics from Fudan University in 2007 and MSc degree in electrical engineering from University of Florida in 2009. He received a PhD degree in electrical and computer engineering from Cornell University in 2014. He has been with the Department of Electrical Engineering and Computer Science, MIT, since July 2014, and is now the associate professor there. His research group at MIT focuses on RF to photonics, integrated circuits and systems for spectroscopy, metrology, imaging, quantum sensing, processing, broadband and secure communication. He was the recipient of Cornell ECE Director's PhD Thesis Research Award, Cornell ECE Innovation Award, and the 2 Best Student Paper Awards of IEEE Radio Frequency Integrated Circuit Symposium in 2012 and 2017. He's also the recipient of IEEE Microwave Theory and Technique MTTS Graduate Fellowship Award and the IEEE Solid State Circuit Society Pre-Doctoral Achievement Award. He is an associate editor of IEEE Transaction on Very Large Scale Integration System and IEEE Transaction on Quantum Engineering. He's also a guest associate editor of IEEE Transaction on Microwave Theory and Techniques 2019. He also served on the Technical Program Committee of IEEE RFIC Symposium from 2017 to present. He's also on the steering committee and the TPC of the 2019 IEEE International Microwave Symposium. He is the IEEE MTTS Distinguished Microwave Lecturer. During the tenure of 2020 to 2022, he won the Intel Outstanding Research Award in 2019 and the National Science Foundation Career Award in 2017. So without any further delay, it's our great pleasure to host Professor Ruonan Han, and I request Professor Ruonan to please proceed ahead and start his presentation. Over to you, Professor Ruonan.
Thank you, Anushirwan. Let me share my screen here.
Sure.
All right, so can you see my screen?
Okay, yeah, you may proceed. Thank you.
Okay, great. Well, thank you for the invitation to this virtual seminar. And actually, at US, I have quite a few friends and colleagues who are from Pakistan. And right now, I will just mention to Anushirwan that I have a Pakistani student, Muhammad Ibrahim Wasik. He is also from UST, and he's a brilliant student. And just this month, actually, what's happening now is the IEEE Radio Frequency Integrated Circuit Symposium, and he won the Best Student Paper Award. So I feel really proud for him. All right, so getting back to this seminar, today I'm going to talk about chip-scale wave-matter interactions at RF to light frequencies. In specific, I will talk about the circuits, the systems utilizing these interactions, and also I will explore some of the applications using these systems. Okay, so first of all, about on-chip electromagnetic sensing. So what I show you on the left is, the major category that we are focusing right now in the field in general, right? So here I show you the automotive radars, the gesture detectors, millimeter wave or terahertz imagers, or even just, the cameras, the visible or IR image sensors. So if you look at all these existing electromagnetic spectral sensing devices, so they basically share quite some commonalities. For example, you are basically using frequency insensitive electromagnetic scattering to detect macroscopic objects in a remote distance, right? So these are the commonalities. But I would argue that another category of research, which is also EM sensing, but it's sort of a complementary to this first category, is rising. And shown on the right, so basically in this second category, what we are focusing on is to use high precision and frequency selective wave and scattering to basically interact with the microscopic particles like molecules or atoms or electrons in the close proximity to the electronics. And we directly interact with the quantum behavior of these particles to perform different applications. Okay, so obviously this second category is well complementing the first category. So here I show you different modalities in terms of the wave and matter interactions. So what you can see in here is, going from megahertz, we have nuclear magnetic resonance, and then in the gigahertz range, we have electronic spin resonance. And then if you can push the frequency to terahertz, you have molecular rotation or vibration and so on. And talking about these wave matter interactions, of course, regarding the quantum behavior, right now the biggest or the buzzword is the quantum computing, right? But I would argue that in addition to the quantum computing, we can actually enable quite some other applications using these interactions. And basically in here, I want to talk about three pillars of applications. The first one is material identification, because utilizing this unique wave matter interactions, we can basically generate quite some unique fingerprints of the materials. For example, in this case, this is the rotational spectroscopy, where you use the wave to excite the rotation of molecules. And you can see that using a spectroscopy setup, we can basically have quite some very sharp transition lines in the result. And these lines are so sharp or so narrow that they serve as the fingerprint. Okay, in this case, it's acetonitrile. So by using these spectrometers, you can basically identify materials. And the second category is sensing, because many of these quantum transitions of particles could be very sensitive to the external disturbance. In this case, we detect the spin resonance of electrons. And as you know, when you have an electron spinning in there, it has a very large magnetic dipole. And now if you apply a strong magnetic field from the outside, this magnetic dipole will basically react. And in terms of the energy, you will start to have what's called a Zeeman splitting of this electron energy. So the split amount is linearly proportional to the external magnetic field. So by detecting the energy split amount, you can translate into how much external field you apply onto the system. So you have a magnetic sensor. And the third pillar is metrology. In comparison with the electron spin, there are quite some other quantum transitions of particles that are actually very insensitive or very robust against external disturbance. For example, in this case, again, this is the rotation of molecules. where you have a positive charge and negative charge in this molecular structure. And when they co-rotate together, what you can imagine is the resulting current actually cancel each other, and then you have very small magnetic dipole. Okay, so that means this system is very robust or insensitive to the external magnetic field. And that also means the quantum transition frequency in this case is very stable. Okay, so in this case, the line width of the transition is only a few hundred kilohertz, but the center frequency is a few hundred gigahertz. So you have a very, very sharp but stable line in there. So now if you just imagine that if we lock our output of the electronics to this physical invariant, then we basically have a very stable clock, right? Similar to atomic clock. So this makes very good metrology systems. So obviously, people want to utilize these interactions and enable some practical systems. And here I show you a few examples. So obviously, these examples are very big and also very costly. So it's not really designed for our daily life. And obviously, one big motivation is to shrink these devices down to chip scale so that we use integrated circuits to enable the similar applications. But now things become really cheap and also very portable. And obviously, there are quite some research in the recent years that target at this goal. And some of these applications and systems are from my own group. So in the rest of this talk, I will give you basically the introductions of some of these words to show you how this is ongoing. So here's the outline of the talk. I have just introduced the overview of this wave-matter interactions, and then I will give you 3 examples that match precisely those 3 pillars of applications that I just introduced. The first one is a Terahertz rotational spectrometer for gas sensing. And the second one is a chip scale molecular clock for the metrology. The third one is a room temperature CMOS quantum magnetic sensor for sensing. Okay, and then I will conclude the talk. So first of all, let's take a look at rotational spectroscopy. So here's the basic principle for the rotational spectroscopy. And what happens in here is, we have many molecules in the gas phase, and they have a polar structure, meaning that you have either electrical dipole or a magnetic dipole in this molecular structure. And now if you shine an EM wave onto this molecule, you start to exert a torque onto this molecule and make it rotate. And it turns out that the energy of the rotation is quantized following this equation. And J in here is the quantum number. And if you just calculate the transition from one stage to the next stage, then the resonance frequency for this energy is actually expressed in here. And what you can see is as you change the J from 1 to 3 to 4, then basically the frequencies are actually equally spaced in the spectrum. Okay. So to give you one example, in here I show you the rotational spectrum of this molecule, carbonyl sulfide or OCS. And what you can see is that indeed these transition lines are equally spaced, and the distance is or the spacing is about 12 gigahertz. But then what you can say is, okay, you know what? Then I can pretty much detect this rotational spectroscopy in the microwave or millimeter wave range. Okay, so why do you talk about terahertz in here? Well, the fact is, as you can see in here, as I increase the quantum number J, it turns out that I have more degenerated substates on each J level. And once you have more empty states in this energy state, and now you make the transition from one to the next, then you basically have more available, states for you to absorb the energy, right? So, and then the transition intensity or the line intensity becomes higher, and that's very good for your sensitivity. So that's why once you push the frequency up or you have more J, you basically have, higher and higher transition line intensity, and that's good. However, at some point, what we can see is that the transition saturates or, plateaus, and then going forward, we actually have a smaller transition. And why is that? And that's because now the Boltzmann distribution kicks in, which tells us that, when you have higher energy, then basically, although you have many empty states on this energy level, but the probability that the molecule occupies this stage to begin with is much smaller, okay? It decreases exponentially, and that basically means that now you have a much less chance to be in here and then jump to the next stage, okay? So that's also why going above a certain level, then the intensity drops quickly, okay, which is shown here. So if you combine these two facts together, now we can claim that the peak rotational mode absorption basically happens in the terahertz range or the sub-terahertz range, and that's why we want to use terahertz spectroscopy to detect these rotational modes. And here we did some measurement by ourselves by looking at the dependencies between the pressure and the absorption, and then this is called Fu with half magnitude. Or you can understand it with just, the line width of my transition line. And at some optimal pressure level, what you can see is that the line width of the transition, as I mentioned before, is only a few hundred kilohertz, while the center frequency is hundreds of gigahertz, in this case, 267 gigahertz. Okay, so we have a very high Q relating to this transition line. And now what you can imagine is if I use it for gas sensing, for example, I have many transition lines coming from different molecules, and the chance that two different transition lines have overlap is very, very small, right? Because each one is very, very narrow. So that's very important and very good for gas sensing because, you don't make mistakes, you don't have false alarms. And normally the chemists call this property to be absolute specificity. Okay, so that's very important. And of course, as I said before, the transition line itself, especially the center frequency, is also very stable against environmental changes, and that's good for metrology. So let's first focus on the gas sensing part. And here I basically show you the rotational transition frequencies of some of the molecules that we are interested in within just 200 gigahertz to 300 gigahertz range. And what you can see is that within this range, I already have many interesting molecules that I want to sense or smell, right? Because these molecules are either toxic or flammable. So now if you have a sensor that can simultaneously sense or detect all of these molecules at the same time, it will be very useful. For example, for air quality monitoring, for breath analysis and health detection, that's very important. And people have already tried to make such a terahertz rotational spectrometers. And here I give you one example, which is from Ohio State University by Professor Frank DeLucia. So the basic idea in here is that people normally use very expensive, these discrete microwave component from, in this case, VDI, to generate the terahertz wave and to receive the terahertz wave. And of course, on top of it, you need to put a lot more baseband circuits and, gas absorption cell, and then you make the whole thing. And eventually, the smallest that people can make these days is like the benchtop size. Okay, it's still very amazing, especially the sensitivity is really high. Okay, this is a 2 part per trillion, so it's very high sensitivity. But it's still very hard to use for normal people. And as I mentioned, our focus is integrated circuit solutions. And then the number one concern is, whether the silicon transistors are able to handle such high frequency, right? And here I show you the measured device Fmax of different transistors. And what you can see is, although most of the transistors are pretty slow, but if you pick up the right technology node, for example, in our case, 65 nanometer CMOS, the transistor speed is still kind of a decent, okay? And especially nowadays, since now, we have a 5G and maybe beyond 5G communications, the major foundries have more focus on the device. And now, for example, our collaborator in Intel, they use a FinFET transistors at 22 nanometer node, and they have a Fmax of 450 gigahertz. Okay, so things are improving. And you can also see that improvement from this chart in here, which shows you that, now at, the low terahertz range, we are able to generate several milliwatt of output power or radiated power. Okay, even at 1 terahertz, my group is able to generate about 100 microwatt of power out of a silicon chip. So, the argument in here is a CMOS chip or silicon chip should be able to handle this. But there's also another concern on the architectural level, which is, the sensing speed. Okay, so normally people use a single tone and they just, sweep this tone across a broad frequency range to generate the receiver, the absorption spectrum. It's very straightforward, but now the problem is, once you do this, it's very slow. Okay, because keep in mind that the bandwidth you need to cover is about 100 gigahertz in order to have a wide detection range. But because the transition line is very sharp, you need to scan at a very good resolution. Okay, so normally it takes like an hour or two to fully cover this entire range, and that's not quite acceptable. Okay, but people use this architecture to demonstrate some nice sensors already. For example, this one is from University of Texas at Dallas, and this is a single tone transceiver at 200 to 250 gigahertz, and they are able to demonstrate some absorption spectrums. Especially in this case, this is the sample from our breath. However, we took a very different let me jump this slide. Oh, yeah, to here. So, however, we took a very different scheme to do this detection. Okay, so in this scheme that we proposed, what we have is actually 2 identical CMOS chips on 2 sides of the gas sample, and each CMOS chip is able to radiate 10 equally spaced frequency tones from one side, and also receive the other 10 tones generated from the other side inside the chip. Okay, so altogether you have 20 tones that simultaneously scan this 200 to 300 gigahertz range, and then these 2 chips, and we call that CMOS terahertz cone chip because the shape looks like a cone, and then these 2 chips simultaneously generate 20 IF signals that represent the absorption of the gas, within this 20 subbands. And then, we are able to basically detect the absorption information of the gas within this frequency range. And the benefits is obviously very clear. Now you have 20 lines simultaneously scanning this band, and then you have roughly 20x increase of speed. But more importantly, if you take a look at the architecture in here, where we use dedicated transceivers with its own built-in antennas in here to detect the incoming wave and also to generate another wave, then each transceiver only needs to cover a very narrow frequency range. Okay, in this case, only 10 gigahertz. So that means we can use quite some interesting circuit techniques to make sure that the transceiver does not suffer from this trade-off between large tuning range and also peak performance. Okay, so that's actually very important. But obviously, the trade-off in here still is that now you need to have 10 transceivers on the same chip. So each transceiver needs to be very compact and also energy efficient. Okay, so obviously there are quite some circuit design technologies that should enable such compact and efficient circuit. Due to the limited time, so I will not focus on the how this core circuit is designed in here because that's a little bit outside of the scope in here. But if you're interested, feel free to go to the papers that we published and look for the details of the circuit design. All right. But basically, this is the result of the chip. Okay, so inside a single CMOS chip, we are able to integrate 10 sub-terahertz transceivers, 9 frequency mixers, 40 amplifiers, all operating at 100 and above gigahertz, and the total size is only 6 millimeters square, and the DC power is 1.7 watts. This one is based on TSMC 65 nanometer CMOS process. And here are some measured results. So the EIRP is about 0 to 10 dBm, and the total radiated power from these 10 subchannels is about 5 milliwatts. And more importantly, as I mentioned, because now we use dedicated transceivers to basically handle each subchannel, we really don't have this fractional bandwidth versus the RF power trade-off anymore, as in the other works. Okay, so now we have a good performance on both sides. Here's the measured output spectrum. The noise figure from these 10 channels range from 15 dB to 20 dB, and for terahertz electronics, that's pretty encouraging numbers. And lastly, we demonstrate the spectroscopy. So in this setup, we have gas chamber in between, and we have 2 comb chips on the 2 sides. It turns out that without any gas in the chamber, the absorption-free overall signal-to-noise ratio for 1 Hertz bandwidth is about 98 dB, thanks to the high power of the terahertz wave and also the good sensitivity. So this gives us a lot of room to play in order to detect the very low concentration gas. And here's a demo. So basically in this demo, we have a gas mixture of carbonyl sulfide and also acetonitrile with a certain volume ratio, and we inject it into the gas chamber. And what you can see is that the CMOS chip is able to generate all these very fine fingerprints of different molecules at different frequencies, and all these transition line frequency and amplitude pretty well match, all the existing database that the chemists have generated. So that basically tells us that we are able to have a very good detection range. Actually, any polar molecule that is heavier than hydrogen cyanide can be detected. And also because the line width is so narrow, we have the same absolute specificity. And the detection sensitivity is part per million level without any gas pre-concentration. Okay, so normally the gas sensor has some pre-concentrator so that you take out the oxygen and the nitrogen so that the concentration of the molecules that you are interested in is higher. But we don't have that. So if we have that standard pre-concentrator, then the sensitivity could be as good as sub ppb level. Okay, so or part per billion level. So it could be very, very sensitive. All right. So now we see how a CMOS terahertz chip is able to smell. Now we can use pretty much the same principle and use the chip to basically do the timing. Okay, so this is what we call chip scale molecular clock. So during our experiment for the gas sensing, we noticed that the transition lines are actually very narrow, as I mentioned, especially for some molecules like this OCS. What you can see is the center frequency can be as precise or accurate as something like this. Okay, so you have many, many digits in there, and they just don't change over different frequency, over different pressure or different temperature. And that's very important because if you use this number, this invariant physical constant, as your frequency reference, then you have a very stable clock. And that's why atomic clock is way better than crystal oscillators, right? So because, this one is based on the same principle. And just for your information here, I gave you some very simple comparisons between different frequency references or clocks. And what you can see is if you use crystal oscillators, where you don't care too much about stability, but you want to have low power and low cost, then you can basically enable like cell phone or computing applications. But if you want to do, for example, base stations for the cell phone communications or navigations, or power grid, something like that, GPS, then you need to have much better stability, okay, like 10 to the minus 10, 10 to the minus 12, or even better, and then you have to use atomic clocks. But atomic clocks consume hundreds of watts of power, and also they tend to be very expensive and also very big. But nowadays, people really want to break this trade-off. simply because, now in many applications, for example, 5G networking, we really want to synchronize different base stations together in terms of not just the frequency, but also the phase or the time, okay? So you need to have very precise local time holdover clock in there. As we know, the 5G base stations are normally pretty small, and also they have to be power efficient. The normal clocks are, not quite favorable anymore. All right. So just for your information, in many cases, you want the stability of the clock inside to be better than 10 to the minus 11, okay, across like 1 hour of duration. And that's very challenging to do. So people tried quite some different approaches. For example, in this case, people tried to generate what they call chip scale atomic clock. And I sort of call this to be the masterpiece of engineering, because what they do in there is to literally just shrink all those necessary components from atomic clock down to a very small form factor, okay? But the principle is pretty similar. And indeed, the stability is still pretty good, okay? It's about 10 to the minus 11, and it burns only about 100 milliwatt of power, okay, with such a small size. So that's really encouraging, but the problem is, as you can see from this graph in here, it adopts very complex electro-optical constructions, and as a result, things are not very reliable, and also you have, a few $1,000s of cost nowadays if you want to buy it. So our proposal is that, now since we have this terahertz spectrometer, which can detect the rotation frequency of molecules, we can simply just use a single CMOS spectrometer chip to do the same work. And we don't use atoms in here. Rather, we use molecules, and we conceal these molecules inside a normal waveguide, single mode terahertz waveguide. And then we send a wave into this waveguide to detect the rotational speed or the frequency of the molecules. And then we create a feedback control loop to regulate the output frequency of the crystal in here, and then we still have a clock, okay? So the benefit is actually very obvious. This is a fully electronic operation, and as a result, you have a very simplified construction, okay? And things could still be made very small. And more importantly, because we use CMOS spectrometer in here, the cost is very low, but at the same time, the stability or the precision is still very high. So there could be quite some benefits out there. But it turns out that we are not the very first group thinking about a molecular clock, okay? It turns out that even before the invention of atomic clocks, the researchers in US have already studied molecular clocks, and in this case, they studied the vibrational mode of ammonia at 23 gigahertz, and they use that as the reference, as you can see in here, okay? But the problem is, as you can see from this graph, the absorption intensity of ammonia at this low frequency is still way worse or way smaller compared to the absorption of molecules that we use at sub-terahertz level. So they have to use a very long waveguide to do the work, okay? And also, since the waveguide frequency is low, the cross-section of the waveguide is also very big, okay? And also, it turns out that, ammonia transition is quite messy. As you can see in here, we have many transition lines that are close to each other, and they interfere with each other, okay? Versus if we use, in this case, carbonyl sulfide at sub-terahertz, the distance, as I mentioned, between each line is 12 gigahertz. So things are really far apart, and then we have a much cleaner transition, okay? So we believe this should be the sort of the renaissance of a molecular clock, and that is enabled by modern days technologies. All right, so to verify this idea, a few years ago we used still lab scale instruments with a custom designed hermetic gas cell with a single mode waveguide inside to test this idea, and indeed it works. And the measured Allen deviation, as you can see in here, is about 10 to the minus 11 at 1,000 second. And what you can see is it's much better than the crystal oscillator, okay? Crystal oscillator, as we know, over time, it starts to drift due to temperature fluctuations and the other things. So this is much better, okay? So this verifies the idea, but still, the question is, whether this is just a scientific fiction or fact, because it's still unknown that whether we can shrink all these electronics down to the chip scale, right? And 3 years ago, we demonstrated the feasibility by literally just placing all those electronics, the terahertz phase-locked loops and all the high-precision baseband control, the terahertz detectors, locking amplifiers, everything onto CMOS, okay? And we also use our custom-designed terahertz waveguide to conceal the OCS molecules inside, and then we make this clock. So basically, in this clock, the probing the probing wave adopts FSK modulation, and in specific, it jumps back and forth on the two shoulders of this narrow transition line, and then we compare the absorption intensities. And based on which side is taller, which side is narrower, like lower, then we can adjust the center frequency to make sure that eventually the center is locked onto this center point in here. Here are some more details just for your understanding. So as I mentioned, we use FSK modulation so that the probing frequency constantly jump back and forth on the two sides of these two shoulders. And suppose in the first case in here, if my center frequency or the average frequency aligns precisely with the center of this transition line, then we don't really see fluctuation of the absorption, right, over time. And now at the output of my locking detector, I generate an error signal that is 0, essentially telling me that, okay, you don't have to change anything right now, you are at the right position. But in the second case, suppose my averaging frequency is higher than the valley, smaller than this valley frequency. And now if I jump back and forth on the two sides, what you can imagine now is I have a fluctuation of the absorption, and the fluctuation frequency is the same as my FSK modulation frequency, and that can be detected by this locking detector, and then it generates a negative error signal telling me that, okay, you know what, you need to pull this center frequency upward a little bit, right? So that's how the feedback happens. And in the third case, if the averaging frequency is higher than this center, then as I do the FSK modulation, I also have fluctuation in here, but with the opposite phase. And that can also be detected by the locking detector, which generates a positive error signal, telling me that it's too high, you need to pull back. Okay, so now if you think about this operation, essentially what I do is I have a small deviation in the X scale, and then I generate the difference in the Y scale. So literally what I'm doing here is as if I'm taking the first order derivative of this transition line. Okay, so if you use the X scale to be the center frequency FP in here, and the Y scale is this error signal in here, and if you do the plot, which is shown on the right, then what you can see is as I sweep, I basically generate the first order derivative of this transition line. And obviously, using this feedback loop, our goal eventually is to lock at the center zero crossing point of this what we call dispersion curve. Okay, so generating this dispersion curve is important, and eventually we lock at this zero crossing point. And here is the package of this chip scale molecular clock. So what you can see is that the size is about the matchbox size. And because we have, the connections to the vacuum systems, we have to make this thing this big. But in reality, the actual encapsulated OCS gas inside the waveguide is about 80 millimeter cube. So it's actually pretty small size. And the DC power of this chipset, including the transmitter and the receiver, is only 66 milliwatts. Okay, and what we can see in here is that indeed, using this chip, we are able to plot that dispersion curve of the molecule, and the measured Allen deviation is about 4 times 10 to the minus 10. So it's a decent number, but it's not as good as our instrument-based clock. And there are a few reasons for that. One major reason is that it turns out that the actual profile of the transition of the molecule is not as good as what we thought. It turns out that, you know, the setup still has some finite frequency response or uneven frequency response, and that creates a tilting of the baseline. So the actual profile is the superposition of this tilted baseline and this ideal transmission line. Okay, so now you have this sort of a rotated or tilted profile from the gas. And now if I take the first order derivative of this line, which is the superposition of these two curves, now what you can see is that this tilting of this straight line essentially generates an offset after you take the first order derivative, okay? And this offset is actually temperature dependent. And that's why eventually when you do the zero crossing locking in here, the zero crossing locking frequency is also drifting over different temperatures. And that's why we have, you know, a degraded frequency stability in here. And our solution is actually pretty straightforward. We realize that instead of taking the first order derivative, if I take the high order derivatives, okay, for example, third order derivative, then this effect of this baseline tilting becomes zero, right? So if you take the first order, you have an offset, but then if you take the second order and then third order, that constant offset becomes just zero, okay? So now we don't have this temperature dependency anymore, okay? And of course, that requires quite some change in the architecture of the circuit, because now you cannot do FSK, which is two discrete point anymore. You have to do FM modulation. So you have to continuously sweep across this transition line to generate all those harmonics. And the goal is eventually we want to lock at this zero crossing point of the third order harmonics or third order derivative of this transition line. Okay, so to enable that function, here's our second generation molecular clock in the same CMOS process. And also we managed to put the transmitter and the receiver on the same CMOS chip. I would not go through the details of the architecture, but you have already known the basic principle. And also another improvement that we have on the chip, and that's probably more interesting to the MTT Society, is that we also managed to have a chip integrated chip to waveguide coupler. Okay, previously we have some off-chip transition for that coupling, but now we managed to directly radiate the terahertz wave from the chip through the silicon substrate of the chip and then directly into a waveguide opening on the back side of this CMOS chip. Okay, so now you directly just put the chip onto the waveguide gas cell and then you're done, as you can see in here. So that increases the efficiency of the coupling by a lot and also greatly simplifies our assembly. Now the size is about a bottle cap size, so it improves a little bit, and also the DC power is still about 70 milliwatt. And here are some measure results. I will skip this. But in here, you can see that the CMOS chip can now generate the third order derivative or the third order dispersion curve of the transition line. And compared to our first prototype, which is this one, which is this curve in here, now the new Allen deviation or the stability of the clock improves, you know, on different ends. And, you know, at 1,000 seconds, now the new Allen deviation is about 4 times 10 to the minus 11. Okay, so we improved by 10x. And actually in our newest molecular clock prototype, which is our third generation, we further increased the stability down to about 10 to the minus 11. And also we can extend that stability to 10,000 seconds. Okay, so now you can maintain that stability for a longer time. So now we finally close up the performance gap between molecular clock and all these chip scale atomic clocks, which are more expensive or much more expensive and also, you know, less reliable. So I think this could be a very promising solution. And in the end, we also demonstrate that the temperature stability and also the the sensitivity to external magnetic field, all these basically improve a lot. Okay, so now that we talk about how the chip can smell, how the chip can do the timing, lastly, let's see how the chip can basically do the magnetic sensing. Okay, so this work is a result of a collaboration between my group and Professor Dirk England's group at MIT. So when we talk about quantum, obviously, as I mentioned, quantum computing is the buzzword right now, and there are quite some different materials and qubit technologies that people are considering, and I show those in here. And what we are interested in is this one. It's called the impurities in diamond or silicon. Okay, so this qubit or this quantum material turns out to be very good, not only just for cryogenic space or cryogenic temperature, but also it's very good for room temperature, which is our interest. And people actually use this material, which is called nitrogen vacancy centers in diamond, for sensitive detection of magnetic field. And there are quite some benefits of that. First of all, as I mentioned, it's sensitive. You can reach even to like picotesla per root hertz level if you have sophisticated instruments, and also because we literally have many of these little qubits inside the material, so the spatial resolution is very high. It could go down to like nanometer scale. So people literally use this technology to even do the magnetic imaging of very fine structures. For example, you can detect the magnetic field coming out of bacteria. Okay, so it's very sensitive and the spatial resolution is very nice. But what I like the most is that because this is the defects in diamond or silicon, in this case is diamond, so it's solid state, which is much easier to handle, and also it's room temperature operation, as I mentioned. So here I show you the comparison of different magnetic sensors. As we know, normally people use Hall sensors or flux gate. They are small, but the sensitivity is not very good. On the other hand, if you use quantum-based magnetic sensors like atomic vapors, the cryogenic superconductor-based sensors, or in this case, NV centers in diamond, then you have much better sensitivity, but normally they are very bulky and hard to use, something like this. Okay, so the idea is we also want to bring these onto a chip scale system. So let me just quickly go through the physics principle of how this thing happened. So first of all, we have a piece of diamond, and as we know, it's literally just like a carbon lattice, right? And what the NV or nitrogen vacancy centers is basically we replace two nearby carbon atoms with one vacant empty state or empty site in here, and also one nitrogen atoms. Okay, so you have N and V in here. And it turns out that once you have this structure, you have a very nice two-level systems. Okay, so in this case, this is the ground state, and I have ground zero and also plus minus one state. And these two states are normally degenerated, so they have the same energy. And the difference between the zero state and the plus minus one state is about 2.87 gigahertz. So normally we don't know how, like, where the electron is, okay, whether it's in the zero state or plus minus one state. But normally what we can do is if we shine a green light onto the diamond so that we excite the electrons from the ground state to the excitation state. Then after the shining, these electrons will relax back to the ground state. And depending on the initial state you are, if you are initially at the zero state, then when it relaxes back to the ground state, it will emit a red light along the way, so you have red fluorescence. But initially, if you're at the plus minus one state, it will also relax back, but it will relax through an intermediate state, which has much less fluorescence light. Okay, so now what you can imagine is if I have a setup where I have, green excitation, and also I have a microwave magnetic field to excite the electrons from this to here. So this magnetic field in here should be at about 2.87 gigahertz. And now, and also at the same time, I use a photodiode to detect the fluorescence. Now what you can imagine is as I do the sweeping of this microwave field, initially, if my frequency is not right, then I don't excite the electrons onto here. Rather, the electrons will all stay at the zero state. Then I basically experience, or I see, a strong red fluorescence light. But when your scanning frequency hit this 2.87 gigahertz, so that the electrons jump to the ±1 state, then the red fluorescence light you detect is much weaker, right? And then if you go off the resonance again, you have a stronger red fluorescence light. So this is called optically detected magnetic resonance because it tells you when you basically have that quantum transition for the electrons from 0 to ±1. But as I mentioned, electronic spin resonance is very sensitive to external magnetic field. So now if I have a strong magnetic field from the outside, then that can split the energy of ±1 so that they are no longer degenerated. Okay, and the difference of this split is linearly proportional to the magnetic field component on this, or the projection of the magnetic field on this NV axis, okay, because magnetic field is a vector. So now if I do the same ODMR scanning, what you can imagine is now I can observe two dips, and the distance between the two dips is basically linearly proportional to the magnetic field along this NV axis, and I can easily just measure what that BZ is. Okay, so this is how we can make a magnetic sensor. But don't forget, inside a silicon or diamond lattice, we have 4 possible access, so that we have 4 possible NV access in the lattice, and that basically means that if I have an external magnetic field vector, that vector will in general have 4 different projections onto these 4 different lattice directions. And that means in reality, if I do this ODMR scanning, I will have 4 pairs of splits in this frequency spectrum. And the difference between each pair essentially tells me the magnetic field projection onto that lattice axis. Okay, so in another word, it means that by using just one sweep, I'm able to measure the vector field of my magnetic excitation. So that's actually very powerful. All right. To enable these operations, a few years ago, we demonstrated a CMOS chip with pretty straightforward structures. So in here we have a phase-locked loop to generate this 2.87 gigahertz frequency, and we use our on-chip loop inductors to launch this microwave magnetic field onto a piece of diamond that is placed on top of the CMOS chip. And we also use basically the metal grating, which is also based on the CMOS metal layers, to do the optical filtering. Because if you do a green light excitation from the outside, although you generate some red fluorescence light, but that fluorescence light intensity is still much weaker than the remaining green light. So you want to take out those green light so that it doesn't interfere with your photodiode. And this CMOS chip has all of those. And indeed, eventually we are able to see, for example, in this case, if I apply an external magnetic field, I can indeed see that 4 splits, okay, 4 pairs of splits in the output. And that's actually a vector-based magnetic sensor. The measured sensitivity is 32 microtesla per root hertz, which is not so great. And later on, we improved the architecture so that now we can excite many more NV states inside a piece of diamond across a bigger area so that we have more signal. And also to suppress the green light further, we also have multiple grating layers inside the CMOS chip, so that we can let more red light to go through and much less green light to go through, and the combination of these two effects essentially give me a much better signal to noise ratio. And because of that, now we can improve the sensitivity by about 100 times to now 245 nanotesla per root hertz. And here's the demo. Okay, so because we use laser in here, we have to place the setup behind this curtain. But what you can see is now when a student hold this permanent magnet and just move around on this sensor, then the sensor can generate in real time, can generate where that magnetic field is sensed. Okay, so now we have a vector field measurement capability using solid state and also room temperature quantum materials. In the future, if we use a higher density of the NVs and also larger area, we should be able to reach about sub nanotesla per root hertz sensitivity, which could be very, very competitive. All right, so I think we are on the top of the hour, so I will stop here. To conclude, in this talk, I show you how we can use low-cost CMOS chips to utilize the wave matter interactions. Okay, and by using that, we can do gas sensing, we can do stable timekeeping, we can do magnetic sensors, and of course, people also demonstrated a lot of promising results for quantum computings. So I believe this area that utilizes this wave matter interactions is just the beginning. Okay, so there are quite some more opportunities waiting for us to explore. So I definitely welcome more young researchers to join this this game, and hopefully very soon we can make it very flourish. Okay. So now I would like to thank my students and my collaborators and also the sponsors. So I would like to just maybe stop here and take a few questions. Thank you.
Thank you very much, Professor Ruonan, for a very interesting talk. So there are a couple of questions. So first question is related to the reliability of these. For example, if you talk about molecular clock, chip scale molecular clock, so how reliable are these devices as compared to the conventional devices?
So I think there's a difference between how reliable the current prototype is and how reliable it's gonna be right in the near future. So of course, right now these chips are basically the results or the the products of our research groups. So sometimes they still have some reliability issues in terms of if the temperature is too high or if the temperature is too low, then it stop working, or over time we have some too much current in some wires, but in general they are very reliable. So as you can see, as I mentioned, now we can run our clock at basically we can generate the stability curve at 10,000 seconds, meaning that the clock needs to run for at least quite a few days, and they don't give any problem. But I think more importantly, it's really about the future. Once these technologies are commercialized, then the stability or the reliability will be as good as the chips inside our cell phones or computers, right? Because literally they use the same CMOS technology, and that's not a concern. We basically need more research onto the gas cell itself, because we need to make sure that we don't leak the gas, or the surface of this single terahertz mode waveguide is good enough so that it does not absorb the gas temporarily, or release some unintended gas over months or over years. So there are quite some more engineering work required, but compared to the atomic clocks, because the construction is so simple, so that definitely increases the reliability a lot.
Right. So as you mentioned in your answer, the how long you see the commercial products such like this, so in a future run, so how many years do you think it will take for them to become commercial?
My assessment is some of these will happen pretty soon. Okay, so at least I think the chip scale molecular clock could be commercialized soon, because I don't see much technological barrier out there anymore, and you know, it shows a lot of benefits in terms of the cost and in terms of the performance. So I would say, you know, maybe 5 years down the road, we will start to see some of those. The gas sensor, the first example, could take a little bit longer, not because of the terahertz electronics, but actually because of some other components. Okay, so for example, it requires, and that's similar to the other spectrometers, it requires some low pressure. And you need a pump, not in general, you need a pump to decrease the pressure down to the desired level. And the pump is normally big and, you know, say a few $100s. So that becomes the bottleneck, because normally the terahertz electronics are the bottleneck. They are very expensive, they are big, but now we shrink it down to the CMOS chip. So it's no longer costly. It's only maybe 10 cents and very small, but you know, we still have to work on the other components to make sure that those are also much smaller, so that the whole combination can be used inside like some very small and cheap device. So what you can see in here is to eventually make these things happening, we need interdisciplinary research. Okay, we need collaborations among different disciplines, mechanics, you know, electronics, a lot of collaborations to eventually make it happen. So it's a challenging topic, but also very interesting for research.
Yeah, that's very true. Because from your presentation, I can see that the research seems to be interdisciplinary, because it requires the knowledge of maybe pure physics as well, also from engineering point of view, all the engineering challenges. So, so in your opinion, as for engineering students, so what is your message for the engineering student on which thing they focus more if they would like to enter in this research area?
Well, I think for example, for undergrad students, my message is you really have to get a very solid fundamentals. Okay, so you know, do very well in math, physics, you know, maybe chemistry, and of course electronics, you know, control, signal processing. These are very important for you to eventually reach at a very high level of research. If you only focus on some very narrow topic early on, okay, so for example, I see that, you know, quite some undergrad students, they are also very interested in, let's say, circuits, but very early on, they start to ignore the studies on the other topics, even including, for example, electromagnetics, and they only focus on circuit design itself, which could be very enjoyable, of course, but then, you know, they start to have bottleneck down the road. Okay, so I think being very broad and also deep in the beginning is very important, and then it's really about, you know, I think during the actual grad study or the PhD research, you have to be willing to take risks, and you also have to be very open-minded. Okay, you have to sort of believe that as long as you don't see very clear defects or very clear problems of a certain idea, you have to just, you know, take a leap of faith and really just dive into it and try to make it happen. And most of the cases, you know, you will get some decent results. I see that some students could be, you know, pretty conservative. They want to generate some near-term results or publications, but so because of that, they tend to jump into some topics that are mature or even sometimes saturated. And of course, you know, they have a lot of papers to learn, and they can even inherit some of the projects from some senior students, and they can quickly generate some results. But down the road, it becomes harder and harder. Like for our case, when we first had this idea of, for example, the molecular clock, nobody believes us. I even talked to our colleagues in the chemistry department, and they were like, forget about it. Things probably would not happen the way you like, and also, you need very sophisticated electronics, and to log onto that transition line, it's just like fantasy. But I don't see really fundamental problems with that idea. It's just a matter of, okay, there are quite some unknowns. And also, I'm fortunate that the students also are on the same page. They sort of trust this thing. And we took multi-year. Of course, during this time, there are quite some unknowns and a lot of learnings. The students also have to painfully, take the quantum physics class again and, read a lot of books. But gradually, things become much, much brighter because we are pretty much the only competitor or the player in this field right now. And also, when we take time and resources to build up all those test instruments, and not just for electronics, but also for chemistry, the barrier there is pretty high. And then, students really just take their time enjoying what they're doing there. And they don't have to worry about, other people may catch up very quickly, or, this idea will, if I don't publish this idea this month, then it will be, published by somebody else very, very soon. So, you might have some challenge in the beginning, but gradually it becomes much, much easier. So I hope, for some of the ambitious students, this is the path that they can take.
Yeah, really interesting. I think with this very useful advice, I think the students who are hearing this seminar will be encouraged to follow this path so that they can be more productive down the line. So with this message, I conclude this session, and thank you very much, Professor Rohan, for your very interesting talk, and hope to meet you sometime in physically as well, or maybe on some other webinar as well. And
Absolutely.
Thank you for sparing the time. Thank you very much.
Okay.
Thank you. Have a nice day. Bye-bye.
Bye-bye.
Thank you, audience. Bye-bye.
Bye-bye.